So I talked about state space representation and what it signifies and how do we obtain state space representation of different systems. We took an example of electrical network yesterday and obtained the state space representation or state variable representation of the same. So today we'll discuss how to obtain a state space representation of mechanical systems. And for that, we first will try to understand that how do we represent higher order differential equations into state space format. So if suppose that you're given a higher order differential equation. So this was discussed yesterday that the order of the differential equation decides the number of state variables that the system will possess or the number of energy storing elements the system will have. For example, if you look at this particular example, you'll see that this has a third order differential equation, and a third order differential equation means that it will be the system which is represented by the given equation will be having three energy storing elements. And of course, it was also discussed yesterday that higher order differential equations will be converted into linear differential equations. For example, an nth order differential equation will be converted into n first order linear differential equations. So likewise, in this particular example, since we have a third order differential equation, and this differential equation will be converted into first order three differential equations. So you now will try to somehow, and this is required in order to finally obtain a state space representation, because without converting them into first order differential equation, you cannot obtain the required representation, the state space representation of the system. So this is the equation which is of the order 3, and from the order we concluded that we'll be trying to obtain three first order differential equations. Here the output is y and u is the input, and we are required to find the state space representation of the same. So how do we first convert this into three first order differential equation? So we'll try to put some assumptions, and these assumptions are corresponding to the state variables. So for this we will try to, since we are required to eliminate terms like d to the power 3 or d to the power 2, and are required to find an alternate for this which has only power of 1. So we'll try to obtain in place of this like d by dt of something, and again in place of this like d by dt of something. So for this we assume certain variables, since we take the first state variable as x1 and we assume y to be equal to x1, and we then assume y dot dy by dt to be equal to x2. Then again similarly, since we have a third order differential equation, so we are going to assume three state variables x1, x2 and x3, where x1 is equal to y, x2 will be equal to y dot, and x3 will be equal to y double dot. So this is the first step that we will execute by assuming three state variables corresponding to the order of the system, and they will be equal to the variable which is being differentiated, so which is output y here, and thus we assign y as x1, y dot as x2 and y double dot as x3. And now from this relation we obtain a relation among x1, x2 and x3. Since if you remember that state space representation, so I forgot to mention this, yesterday we said that the state space representation is something that looks like this. So x dot is equal to ax plus bu. So this corresponds to the state equation, while the output equation was given by y equal to cx plus du. So whenever you're asked to find the state space representation, it means that you will have to somehow include this answer at the end. So we are required to find a relation between state change and state as well as input, likewise a relation between output and state and input. while A, B, C, and D are matrices, which will be accompanying some associated elements or constants that we also discussed yesterday, and we'll again try to understand it today by solving these examples. So we are required to find the relation in order to convert this into state space representation. We'll try to express this particular differential equation into this form: x dot equal to ax plus bu and y is equal to cx plus du. So after assuming state variables by taking this format, we now write the state variables with a relation among themselves, like for example x1 dot. So if you talk about x1 dot is nothing but d by dt of x1 will be equal to d by dt of y. So x1 dot is y dot. And what is y dot? Y dot is assumed equal to x2, and that is why we have written here x1 dot into x2. Similarly, we write x2 dot equal to x3. Since x2 dot is nothing but y double dot, which is written here, and x3 is assumed to be equal to y double dot, and hence x2 dot is equal to x3. So why have we written this will be clear from subsequent steps. And x3 dot. Now you have x3 dot, which is equal to y triple dot. And what is y triple dot? Y triple dot can be obtained from this equation. So since y triple dot plus 6 y double dot plus 11 y dot plus 10 y is equal to 8u, and thus from this relation you get y triple dot will be equal to you're going to put this values, the remaining values, 6 d square d 6 y double dot 11 y dot and 10 y. You are going to take these three elements on the right side, and thus you get y triple dot. So this is y triple dot will be equal to minus 6 y double dot minus 11 y dot minus 10 y plus 8u. Now since you assumed state variables to be x1, x2, x3, this means that you are going to somehow obtain this equation in terms of state variables or input only. And since y triple dot is nothing but equal to x3 dot, since x3 is y double dot, then x3 dot will be equal to y triple dot, and this is equal to minus 6. So we'll try to convert the terms of y into state variables. So y double dot was assumed to be x3. So in place of y double dot, we are going to write x3. So it's written here, 6 minus 6 x3. In place of y dot, you'll be writing state variable x2. So you get this term as minus 7 x2, which is written over here. Likewise, in place of y, you will be writing x1, and thus you get, or you replace this term minus 10y by minus 10 x1, which is written over here, plus 8u, where u is the input. So we are not going to change, or we're not going to alter this value u, because you have in state equations the input u as a part of it. So you now got an expression. You got these three equations, x1 dot, x2 dot, x3 dot, which are nothing but the state change x dot. So we somehow obtain a relation. We see that we are getting a sort of relation which was x dot equal to ax plus bu, but we still are left with a task of bringing equations, the state equation, into matrix form. So because these are something which are in the form of matrices or vectors, so we acquired the state changes in terms of these states, and this is what was desired. In case of state equation, we required to find the state change in terms of the state, which is x dot in terms of x or input, and this is what we obtained in these three equations. Now we are going to use these three equations to form the matrices or vectors in order to finally obtain the state equation in vector form or matrix form. So using these three equations, we get x dot, which is matrices of x1 dot, x2 dot, and x3 dot. So this corresponds to x dot, which is equal to a times x plus b times u, which is input. So this is the relation that we were required to obtain, and now we are going to populate the matrices corresponding to A and B using these three equations. So if you look at these equations, you see that x1 dot is equal to x2 only, which means that you are going to write element x1 dot equal to 0 multiplied by x1, and since you have only x2 here, so this will be 1 multiplied by x2, and again no other elements except x2, then all other elements should be taken as 0, so this will be 0 multiplied by x3, and then plus 0 multiplied by u. Likewise, if you look into equation the relation to x2 dot equal to x3, in this case you get here as 0, then again as 0, then 1. So this one will be multiplied by x3, and then since you don't have any term of input in the second relation, thus this will also come out to be 0. Likewise, x3 dot can be written from the third relation, which is minus 10 x1. So you're going to populate this matrix, substituting minus 10 here, multiplied by x1, and then you have minus 11 multiplied by x2, so you're going to substitute minus 11 here, then again minus 6x3 multiplied by x3, minus 6 here, and then you have a relation with input of x3 dot, which is multiplied by 8, so the input is multiplied by 8, and this is the required state equation. So likewise, after obtaining the state equation, you are required to obtain the output equation. So in this case, you have output as y. So y is the output, which means that you are going to express the output equation in terms of cx plus du. And we already have identified x. X is what? The matrix of x1, x2, x3, and u is the input. So now we will be writing this in the form of matrix. So y is C. This matrix corresponds to C. This will be x plus d times u. And one important thing, since you have this matrix of state change, which is of the order of 3 cross 1, and again you have a matrix of state as 3 cross 1, which means that the matrix A will always have to be of the order, looking at this element and this element. So because we know that two matrices of order, let's say n and m, the other matrices of the order A cross B. So these matrices can only be multiplied if the value of m and A are equal. Otherwise, they can never be multiplied. And after multiplying the matrices, you obtain a final matrix which will be having an order of n cross B. So this is something that you already know about. So using this idea in this concept, we know that this matrix is of the order 3 cross 1. This is of the order 3 cross 1, and this matrix should always be of the order 3 cross 3, because this element should be equal to the element in order for the matrices to be multiplied, and the final after multiplying the matrices, the final result that you obtain will be having an order 3 cross 1. And since we knew that this is of the order 3, and from this value we assign value 3 over here. So likewise, if you look at the output matrix, since this is a 3 cross 1 matrix, and the output is only a single variable, which is 1 cross 1. So what should be the order of this matrix C? So I need answer from your side. Tell me the order of matrix C. One bonus mark to give the correct answer. So the order of matrix should be 1 cross 3. So the order should be 1 cross 3, because since the order of y is 1 cross 1 and the order of x is 3 cross 1, and in order for C to get multiplied with x, the condition is that these elements should be equal, first of all, And after multiplying the matrices, if you initially assume this as A cross 3 is clear from this value. So after multiplying A cross 3 with the 3 cross 1 matrix, the final matrix that you obtain will be having an order A cross 1. And since you know that the order of Y is 1 cross 1, and thus A should be equal to 1. So the order of matrix C should be 1 cross 3. And the order of matrix D will be 1 cross 1, because U is a single element. So you can say that this is of the order 1 cross 1, and thus to obtain a multiplication of these two vectors having order 1 cross 1, this matrix should also have order of 1 cross 1. Now starting to populate these matrices C and D. So if you look at the equation here, so since we want to find a relation between y and the state variables x1, x2, x3, as well as the input u, so this can be this is clear from this particular equation: x1 equal to y. So x1 is equal to y. If you use this relation, you see that y will be equal to 1 multiplied by x1, 0 multiplied by x2, 0 multiplied by x3, and since there is no input in this relation, you get this 0 as well. So this is the required state space representation of the equation which is given here. So what we did was we identified we converted this third order differential equation into three single order differential equations by assuming state variables in this manner, and from that we obtain relation like this. Now here is an example of a mechanical system. So in the previous example we discussed that example in order to understand how to obtain state space representation of differential equations of order more than 1. So if suppose that you have a system represented by differential equation having order 2, 3, 4 or higher, so such systems can be solved simply by converting the differential equation of higher order into n number of single order differential equations. So we are oftenly faced with such examples in case of mechanical system. For example, if you talk about this particular example, you see that you have a mass attached with a spring. So if you try to write the equation that governs the dynamics of this system after obtaining the free body diagram of mass m, so let's try to obtain it. So force is F is the force which is applied on mass. The resisting force is acting on it is because of K, which is Kx, since x is the displacement that the mass has, and the other force which acts on it is because of the friction. The coefficient of friction is taken as B, and thus this is given as B x dot. The third force which acts on the mass is mx double dot. So these are the three resisting forces which act on the mass m by the force F is applied to it. Now obtaining the relation, so by applying D'Alembert's principle in Newton's law, you will always come to this relation, which is F equal to Kx plus B x dot plus mx double dot. So now we see that this example has a differential equation of order 2. So this is clear from the differential equation that we will, in order to obtain state space representation of this system, we will have to first convert this differential equation into two first order differential equations. And notice that normally when we talk about state space representation, so the nomenclatures that were used for state were x. So since x now in this case is used as output, so you will have to assign some more names or nomenclature to the state variables. So it's not good if you're going to write now x dot equal to ax plus bu for this particular example. This is because you already have assigned x as output or the displacement here. So instead of writing, or instead of obtaining state variables in terms of x, we'll assign some other nomenclatures we'll be using, like for example a, small a can be used, you can use small b or any other terms you like, but these terms should be different from the variables which had already been used in the example or problem. So now we're going to write, we're going to assume one thing more. So I have skipped the part of assumption of state variables as a and p, because of the reason that this example is the simplest of all mechanical system, and thus it was not required to assume the state variables in the form of a and p, and I have skipped that part and straightforward move towards the second step without assumptions. So since one thing more is that in case of mechanical system, you'll find the state variables always as x and v, or displacement or velocity. So these are the two state variables which are always associated with mechanical systems. And this is often practiced in a lot of books, or almost all books used x, the displacement and velocity as state variables. But as I told you yesterday, if any other variable within the system has a linear dependency with x or v, that variable can also be chosen as a state variable. But for the time being, since all the books have been using x and v as a state variable, so we'll be assuming the displacement and velocity, and we'll be using this as a state variable. So we assume the first state variable in the form of v as equal to x dot. The second state variable comes out to be equal to, the state change. So the state change x dot comes out to be equal to v, while this second state change v dot comes out to be equal to x double dot. So this should have been written in the reversed form, but nevertheless. So the state change, since we assume x as a state variable and v as a state variable, thus x dot and v dot are a state change. So we will be writing the same relation of x dot equal to x b, where x corresponds to the vector accompanying x and v. So since x dot is equal to v dot, and v double dot is how much? V double dot, sorry, we are not going to write v double dot because you don't have a third order differential equation here. So you have x double dot. So v dot, this is v dot. And from this equation, you can obtain the relation of v dot in this manner. So f is equal to kx plus bv plus mv dot. So what we did is we substituted in place of x dot, we wrote v, and in place of x double dot, we wrote v dot. And we did this in order to have only one term with derivative in the expression. Had you not written this term in the form of v, or if you had written this as x dot, so let us assume that I left this expression as f equal to kx plus bx dot plus mv dot. So we cannot obtain the state equation from this relation unless we have only one variable with derivative. So either you have x dot, the expressions of x dot only, and all other variables having any relation and any derivative, doesn't have any derivative, or you write this in terms of v dot and you somehow eliminate x dot. So the only way we are left with is writing this expression in terms of v dot and eliminating x dot, or we are going to write x dot. We are going to write a variable in place of x dot which is not a derivative. And we do this because if you look at this relation, what we did in previous example. So we always have a relation of state change with state variables. So we don't have any relation of state change with state change. This is because x dot represents a state change, while x will always represent state and not a state change. Sorry. So this is state, not a state change. And that is why we will try to obtain. So what we did here is we obtained x1 dot in terms of state or input, x2 dot in terms of state or input, likewise x3 dot in terms of state or input. we never obtained any state change in terms of a state change. So that could have been wrong, and we couldn't form the state space representation if we did so. This is why what we are doing here is we we are trying to obtain a state change v dot in terms of state variables and or input. So you won't find any term of state change with v dot as well. And now if you use equation, if you're going to use this relation, which is x dot equal to v, state change equal to a state variable v. So you identified a state variable as x and v. So they are interchangeable. You can write them as v or x. So it doesn't matter at all. It's all up to you, whatever you choose as the first variable and the other as second. So from this relation, we see that state change x is. Sure, please. Yes, please ask. Sorry, I missed this term. Okay, fine, thank you. There should be have been an m here. I missed this. Thank you. Okay. So because you have a element associated with v dot, and this m should be after you take this v dot on the left side, this m should be coming in the denominator of f as well. So I missed this term, so you write it, no problem. So from this relation as well as this relation, so this is again a state change written in terms of state variables and or input. So using these two relations, we are going to populate our matrices A and B. So let me write these relations again. So the output, if you look at this system, so what is output? It's x. So let us assume this output to be equal to y, since in case of the output equation of state space representation, we write the output as y equal to cx plus du. So we obtain the output. Now using these relations, these are the state equation and this is the output equation. We'll populate the matrix A, B, C, D. So for state equation, we have x dot written in terms of AX plus BU. So this is matrix A equal to A into X plus B into U. Using this equation, these two equations, we'll try to populate this matrix. And if you look at this expression, we have V dot equal to minus K by M X. So this term will be written as minus K by M, which will be multiplied by X. And if you look at the first relation, x dot equal to v, so you have sorry, hold a second. So if you look at v dot equal to minus k by mx minus b by mv plus f. Sorry. So we first wrote this relation x dot equal to v. So x dot is equal to 1 times v and 0 times x plus 0 times f. Likewise, if you look at the second relation, which is v dot equal to minus k by mx, so since x is here, so you will write minus k by m here, minus b by mv, so this will be minus b by m times v, and you have input, this was f by m, so you'll be writing here 1 upon m times f. So this is the required state equation. So let me write this clearly. So b by m minus k by m, then 1 f, 1 0 0 f. So this is the state change in terms of state and the input. Likewise, we have output y equal to x. This will be written as 0 and 1 in this manner. But one thing is important, that you will always have to write the same order what you used in state change. So if you first wrote v dot and then x dot, then you will have to write in case of state variables as v and x. If you wrote this as v dot and x dot and you change this as x and v, then in that case you will be committing a mistake. And similarly, so this is important to maintain the order. Now our next example is, I apologize because I ran out of data.